Good morning, everyone. Sorry about the minute delay there. I was trying to get some things moved here. You'll probably hear some crinkling as I have moved some papers that I read from a little bit closer to the mic, just so they're slightly easier to read. But we'll make that work. All right. I have placed up all the homework and the exams. They're scheduled out towards the end of the semester. I haven't done any practice exams. If you want a practice exam, let me know. Email me that. What I've done is I've given 3 attempts on the exam, kind of in lieu of that. And I should say there's 2 exams. There's one's on lines, and then there's the overall final that the department has normally gives. And I can't think of anything else administratively that I need right now. I've been saying it all, and we've been talking back and forth in email fairly well. Yeah, I have a lot of individual questions I get that I've replied to. I have one person I have to send an email out to after this class, which the replying here wouldn't be appropriate. So administratively, that's all I have. If you need anything specific, please email me. And I guess I'll get started. We're about where I planned the semester to be if we were in the classroom and I was covered with chalk. I plan most of the days to be doing stuff in class, like the worksheets. So these lectures are kind of bite-sized, relatively, to what some of my other lectures have to be in the hour and 50-minute class period that we have. The stuff in this last bit, I'm going to do a lot more examples, and I'm only probably going to do a section, 2 sections, in a class period. It's when we start using variables, right around doing the lines, the idea that X and Y, you have 2 variables and you keep them in there, people really want to plug numbers in them. And if you can fight that urge, and start looking at the lines as a form for multiple solutions, and that's the practice that we just went through, is that by having Y equals X, we have this thing that describes multiple solutions, and they all lie on a line. They all lie on a line. Words. That if you have these things that represent multiple solutions, what we move into today, polynomials and many named terms, isn't as intuitive, and probably has more of a conceptual leap than the lines did. So I'm going to rewind a bit and spend a lot of time talking about exponents, multiplying something by something else. And so we had a rule where we had an exponent had a base and a power. We talked about these a little, and they start becoming more and more important in mathematics. Their models get used a lot. And so what we're going to do is, as we talk about these, we're going to see some rules that come out of exponents, and we're going to focus on these rules and how they come together for us. Again, this is kind of, I've tried to, when we were doing the rules of real numbers and we did equations and like terms, I started introducing this because I like the repetition. And we saw bases with numbers. So a very popular idea of a base is 2 to some power, which represents 2 times 2 times 2 times 2. The power says that's how many times we're multiplying. And as I would trip over my tongue, multiple multiplications. And we did some problems where we would make a table and we'd find how, like when a population doubles. And doubling is a very common thing in populations, in growth, in natural systems where I guess the best way I could show growth, a doubling growth usually ends up being cells. You know, of one cell, it's going to break into two cells. Well, each of those cells can break into two, right? Every time a cell copies itself, it breaks into two. And these can be represented by multiplying by some power of 2. Each step in the process is a doubling. And so the exponent is a way of talking about the generations of the cells that go on. And organic things tend to grow that way. I think Fibonacci, back in the first Western culture math textbook, Liber Abaci, in 1202, did a thing with pairs of rabbits. Because pairs of rabbits make more rabbits. And he found a pattern with that. Though he didn't use a doubling principle, he used another way of representing the population growth. And these things end up being very important for people if you're controlling the population of your cattle, if you're controlling how diseases spread or grow. They're based off of this ability to double or to replicate itself. And so this mathematics gets used a lot. And the rules for powers and bases become unique. When we were saying 3 times x, we were saying x added 3 times. Now when we're saying 2 multiplied 4 times, well, this is like multiple additions. And so that extra mental step brings with it some things that we have to take account of. For some reason, I started on the bottom here. I guess I'll scroll up for more space. And so we're going to learn some rules. Now, at this point, we're in the last chapter of the book, so I'm going to use the notation for exponents that they use. We were using bases with b. Because we're going to want our base to be a variable, I'm going to switch this to be x to the n, where we have some variable to a power. And that's what we're going to look at. And we're going to look at the different ways exponents play out mathematically and the different rules that come with them. And so the first rule is an identity. And it's anything to the first power is itself. And so we tend not to write identities. And I think one of the things that if I'm going to, for a little bit here, I'm going to translate the exponent over to the side. All of our multiplications, we have an invisible 1, and then we count how many times we multiply x by afterwards. And so this is saying I have 1x in this list. And that's our identity. I'm going to say null for the 0. If we have something to the 0 power, it's just the 1. And the same rule happens here. I have 1, and I'm multiplying it by, well, 0 x's. I don't put any x's down, so I get a 1. And these are the 2 rules that are going to underpin everything. A thing, if you continue to do mathematics and you're trying to organize your, well, I know you'll continue to do mathematics, but as you do organize the rules and slowly get used to using them and looking at what they mean, you'll notice that most of the rules start out with something we do with 0 and something we do with 1 for whatever the operation we do. 0 and 1 build up all the numbers. And it could kind of go back to the first class. We could build any number we had by adding 1. And then once we wanted to do different types of numbers, we learned how to multiply and divide. And that started to give us the idea of decimals and fractions. And then we found these irrational numbers, and all of a sudden we had all these numbers. But they all start with zeros and ones. We take these zeros and ones and we add, subtract, divide, and we can kind of mutate with these operations, 0 and 1, into anything we need. And so when we start talking about a new thing or a power, there's usually a rule for 0 and 1 underneath it all. Well, one of the things that happens is I can have, so we'll have a multiplication of things with powers. So I have x to some base times, or some to some power, x to some power, sorry about the word choice there, times x to something with a different power. The base has to be identical. So when I multiply the same base to 2 powers, I add the powers together. Now for me, I'm multiplying, but the thing I'm working on is up 1 level from what I'm normally doing. So if I'm multiplying and I'm up 1 level from what I'm normally doing, I remember I have to add. And that's how I actually remember these rules. I kind of look at PEMDAS as a ladder, and when I'm working with powers, I'm a step up on the ladder from what I end up doing. I look to the step before me. Again, but I know we covered this. I know I'm reviewing, and I know I covered it almost in this way. I'm not adding any more to it. Yes, Teresa, x to the 4th would be multiplying x 4 times. And I'll use that in what I want to do down here. So I want to show this as an example in multiplication. So I will borrow the x to the 4th times x squared. I'm not going to use the rule first. I'm going to look at what happens. This is saying I have x multiplied 4 times. That's this one. And this says I have x multiplied twice. Well, these are multiplications, so I don't need the grouping symbols. I can multiply together because my order doesn't matter. Whoops. Got one extra here. Let's see. I have my 2 from up here. There's my 2 from there. And there's my 4 from there. And if I count these, I have 1, 2, 3, 4, 5, 6, or x to the 6th. Well, my addition rule says x to the 6th. And that's why we're adding. We're counting up how many times we multiply. And so if I'm multiplying again, I have to add an additional set of multiplications. And that rule falls out nicely. All right. Well, multiplication has its inverse, which is division. And I'm going to use my PEMDAS idea. If I'm up in a power and I'm dividing, then my rule's probably going to be subtraction. Okay. So if I have x to the 8th, not 8th, wow, English is weird, and x to the b, that is the same as x to the a minus b. let's look at a few of these in practice. So I have 10 to the 5th divided by 10 squared. Now I could convert this, right? I could, if I wanted to 10,000 divided by 100. Let's see. Whoops, 100,000. 100,000. Which would give me 1,000. Always lost a zero. I could do it this way. But if I use my rules of powers, and that this is a division, so I can write it as the upstairs minus the downstairs, which is 10 to the 3rd, which is 1,000. It doesn't just work with numbers, though. It can work with numbers in the form of variables. I can have some unknown quantity p that I'm taking to the 12th power, and through the organization of my laws or whatever I'm doing, I'm dividing by p to the 7th. So I use my subtraction rule. I get p to the 5th. You know, sometimes these things might happen together. Again, right now I'm not giving you specifics for rules. I'm showing the pattern in its application. I might have m to the 3rd times m to the 5th divided by m squared. And so I'll keep the m3rd out front. And then in my division will be 5 minus 2. Notice the order of operations is still working its way through this. I'm doing my divisions and multiplications. So I could, I divided first, then multiplied. Well, since they're equal on PEMDAS, I could multiply first. So I could do m 3 plus 5 over m2, which is m to the 8th, over m2, which is m to the 8 minus 2. Or m to the 6th. I get the same answer because these are equal order of operations. I have a habit of going and getting my divisions out of the way first when these pop up. Now we haven't looked at why particular sets of these things have popped up. We're looking at the rules and how the rules work their way through different exponents. A thing that's going to be useful for us is the base has to be identical. So x cubed times y to the 4th, they don't have the same base. So the best I can write that is as a multiplication of the two things. But the powers themselves don't combine. And watch that. Make sure when you're going into your product and division rules that you are gathering the things with the exact same base. So what can happen is I can have x cubed y to the 4th over y squared, and that means that the x cubed doesn't have anything to match with its base but the y, has a base downstairs that can simplify like this. And so we gather the things with the same variable or the same base when we're using our exponent rules. All right, now here's the weird one. And if we do division over and over again, so let's say I have x squared. And I'm going to divide this by x. So I'm just going to make a series of steps out of this. So I'm going to start, well, I'll start with x cubed. I'll give myself one more so the pattern can hold out. That's the same as x times x times x. I'm going to divide this side by x. I want to divide this side by x, because whatever I do to one side, I do to another. So that makes that x squared. And that's the same as having two of them over here. I'm going to divide this side by x. I am dividing by x each time. This gives me x to the first, which is an individual x. I'm going to divide this side by x. And I'm going to keep my power here. My power rule says this is 1 minus 1. So that's x to the 0. Whatever I do to one side, I do to the other. And over here, I'm going to call that 1. And that's kind of where the idea that anything to the 0th power is 1. But here comes the neat bit. I'm going to divide this by x, which means I divide this side by x. My new power, 0 minus 1, is x to the negative 1. I use my subtraction rule to bring this down lower. And that's equal to 1 over x. Now I'll divide this by x again. I'll divide this by x. I'll write it this way. I have a power of negative 1 upstairs. I have a power of 1, so minus 1 is x to the negative 2. Well, that's equal to 1 over x divided by x, which is the same as multiplying by 1 over x. But we have this idea now that we can have a negative exponent. And it makes sense in the pattern of creating things. If I start with x to some power and I divide by x, it's the same as subtracting 1 from the exponent. Now on my right hand side, it shows me what that is equivalent to and how many x's I'm multiplying by. On my left hand side, I keep track of that with the exponent. What I wanted to do is I wanted to punch through 0. I wanted to see what would happen on the other side of the number line. And so the book states this as a rule: x to the negative a is equal to 1 over x to the a. So this turns powers into fractions. And one of the things you'll find a lot of textbooks ask is that you never use any negative exponents. So if you saw x minus a, you'd put 1 over x to the a. So for example, four to the negative 2 is the same as 1 over 4 squared, or 1/16. It's a compact way of bringing fractions into our exponent rules. This means, though, that sometimes I can get an exponent that's downstairs already that has a negative in it. to write this in the icky way first. That's like 1 over 1 over x to the a. Remember, this is the icky way. It's just to illustrate. And we said division is the same as multiplying by the reciprocal. So this is like 1 times x to the a over 1. Whoops, that should be an equal sign in here. Sorry. Or x to the a. And so something happens that if I have 1 over x to a negative exponent, it comes upstairs. And the book says this is a reciprocal rule. 1 to the x minus a is equal to x to the a. And that's the reciprocal. But what I've tended to find is if you have something with a negative exponent, what it's telling you is you can throw it on the other side of the fraction bar. The negative exponent's like going, I'm on the wrong side of the line. Put me on the other side. Was the voice okay? Right. No, so let's look at a x to the negative 2, y to the 4th, z to the negative 3. All right, I'll make a complicated example to show what I mean here. So this is saying, hey, I'm on the wrong side of the fraction bar. So I should be down here with a positive 2. And this is saying, hey, I'm on the wrong side. So I should be up here with a positive 3. And so the negative signs tell you to go to the other side of the fraction bar. And if you start with just a negative sign, then you have to invent the fraction bar. Right? And you could have a number with you too, 4z to the negative 2. The 4 stays upstairs because the power is not with the 4. And the z comes downstairs with a positive exponent. And so what you'll end up seeing is books will go, please write everything with positive exponents. And what they're saying is if you get a negative exponent somewhere, move that thing to the other side of the fraction bar so that you can have a positive exponent. And if you're like me and you study mathematics and you do this rule over and over again, all of a sudden you start finding that textbooks stop doing that somewhere in the calc series. And you're like, why are we not doing all the things on the fraction bars? And it turns out sometimes knowing the power is negative has some information in it. So what will be nice for us and for us to do is whenever you see a negative power, move the thing the power is attached to, its base, to the other side of the fraction bar, and then you make the power positive. Right? So that's x to the first, but we never write our ones. All right. I'm going to do examples of rules and how these rules come together. So I'm just going to pick some examples from the exercise in the book, and then we're going to finish off the rules of exponents, saving scientific notation for the next time, I think, which is where I wanted to split it. So let's just tend to put some of these together. Am I getting close? Yeah, I'm getting close to this. All right, I'm going to erase my scribbly. Give me a second to erase the board. Sorry for the weird voices. I am in a not enough coffee in the morning mode yet. I will be saying that I actually slept well last night. It has been a while since I've had a fairly restful sleep, which is, it's a normal psychological response to anxiety. A little grumpier than normal. And sleep's not as fully restful. But last night I went to bed relatively early and woke up relatively normal. But still need me a coffee. All right. Yeah. And I'm actually going to focus on some things that we'll learn as we do these. So negative 3 squared. we run into a small problem with negative signs, and so I'm going to do these as an example. I'll compare the two things. All right, these obviously don't look the same, but there's a very subtle difference between them. If you were to enter these on your calculator the way they are, if I go on my calculator and I type in -3 squared and hit enter, I get -9. But if I go into my calculator, I put in a parenthesis, -3, and then I square the parenthesis, I get +9. And we're going to build the rule that shows us why the second one works the way it does. But for here, because the ambiguity is this a -3 squared, or is it 3 squared, take the opposite? Mathematicians have decided that if the negative is not in parentheses, it's not part of the number 3. So this is saying multiply -1 times 3 squared. And order of operations say you do 3 squared first, and then you multiply it by the negative. But the parentheses here are saying -1 times 3 squared. So the entire -3 is squared. And so if I were to expand this out, this would be -1 times 3 times 3. And this would be -3 times -3. And hence that's the difference. And so we'll see that with negative signs as we come across. All right, so let's look at some more examples now that we know what our signs are going to do. And so I'm going to take a -1/2 and I'm going to cube it. You didn't think I would. 1 means to multiply. The dot is the multiplies in here, right? Dot. The -1 is hiding underneath all of our numbers. There is a 1, and so when we have the negative sign, it's the opposite, which would be the same as multiplying by -1. All right, I'm going to rewrite this as a series of multiplications. The power is telling me I'm multiplying 3 times. So a negative times a negative is positive, and a positive times a negative would be negative. So I get a negative. And we have discussed this before. If the power is odd and it's a negative, I get a negative. If the power is even, whatever I do is going to be positive. And we'll see that. So 1/2 times 1/2 is 1/4. And 1/4 times 1/2 is 1/8. Or, if we remember on our fractions, we multiply all the tops. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. And we get -1/8. And I'm going to look at this one other one from the book. We have x to the 12th over x to the 12th. If I use my power rule, because it's a division, I have 12 minus 12, or x to the 0. But anything to the 0th power is 1. This should be reassuring for us because we can talk about division whenever my numerator is exactly the same as the denominator. When I ever am dividing something by itself, I should get 1. Doesn't matter what other mathematics I do to it. Okay, so these rules are consistent. They're tracking for each other and doing the same thing. All right, let's look at the nasty laws now. So I'm just going to write where we've been. X to the 0th is 1. X to the 1st is X. X to the negative A is 1 over X to the A. X to the A times X to the B. We'll add the exponents. So let me put semicolons between each law here. I'm just really doing a condensed summary. I like the semicolon. It's not as permanent as a colon. It's kind of a semicolon. And that's a summary of what we looked at. The other thing we can do, this represents a quantity. And so I can take this whole thing to a power. And there's a rule we can do with this, but let's write out what would happen. Let's use an example. Let's use x cubed squared. That's the same as writing x cubed times x cubed. And my power law says I would add these, so that's x 3 plus 3, or x to the 6th. But notice what happened here. I multiplied this multiple times. In fact, I multiplied it 2 times, which meant I had to do 2 additions of what was under here. When we talked about 2 additions, we said I was multiplying. And so this rule says when I have some exponents to a power, I multiply the exponents. Again, I'll put off to the side in a funky yellow my PEMDAS. And now I'm up here doing exponents, but because I know I'm up above, right, I look down and I multiply. If I'm going to memorize this PEMDAS thing, I'm going to use it every time I can to help me remember all my other rules. So if I have a power to a power, I multiply the powers. I'm going to get as much money out of the PEMDAS rules as I can. All right. So we're going to start getting some combinations of some nice things here. Well, if you've noticed, I've been mixing some variables. I have done x to a power and y to a power. Well, sometimes those two terms coming together can be taken to a power. And that's the same as x times y times x times y, a total of a times. Right? If my power is up there and it's telling me how many times I multiply things, I can multiply this group of stuff a times. But it doesn't matter what order I multiply things in. So I could put all my x's up together. A times. And I could put all my y's together. A times. But if I'm multiplying x's a times, that becomes x to the a. y to the a. So the book says, hey, if I have some set of power or some product, if I have some product and I take the entire product to a power, each of the factors gets raised to that power. And so I'm trying to use our language, trying to go back to things we do, because this can look odd. You know, I could have the product of 3x, but I want to multiply that by 4 times, right? 3x times 3x times 3x times 3x. Well, that gives me 3 to the 4th x to the 4th. What is that? Is that 240? What is 3 to the 4th? 243? Oh no, it's 81. I want one more. I want 3 to the 5th. That's why we have our calculators. Well, we can combine this with a rule that we already have. Notice this is distributing to here and distributing to here. So if I have x, some factor to a power, and a factor to another power, and I'm going to multiply all of these c times, well, that's the same as x a. I'm going to distribute that c to this. And yb, I'm going to distribute the c to that. But this rule up here, well, yeah, says I can multiply those. Come back down here. So I get x ac y bc. And so our powers can distribute to other powers. This actually happens a lot more common than you would think. Right now we're learning the rules, and I would really recommend in the chapter 13 in the book, or I'm sorry, chapter 11 in the physical book. Chapter 11 in the physical book, chapter 15 on the online book, is to do some of the examples in the first 2 sections. That's kind of where I'm pulling these rules from. But it happens a lot that we have some collection of stuff, and we want to raise it to a power. That collection of stuff might not fall out neatly. We might not know what a part of it is. Our variables get used a lot. I mean these look odd, but I'll show you an example of this right here that sometimes makes it easier. If I have 25, let's see, y to the 3rd. And I'm going to take the whole thing to the 5th power. Now there's a couple things I do when doing powers. But in this case, I'm just going to say, hey, this is 25 to the 5th, because the 5 is being distributed to the 25 as a power. And then y cubed to the 5th power. So 25 to the 5th, y to the 15th. Now I'll usually leave it like this until I grab my calculator. Until I get a value for y, I don't always put in all my constants. And 25 to the 5th is like an obscenely huge number. Yeah, it's 9,765,625. It's a big number. But that's how these things distribute. And getting quantities like this are quite common. Well, that quantity we can do other mathematical operations for. What's nice about our power rules is they simplify fairly well for us. And it's their simplification that we're going to try to focus on. One of the more common things, so I was talking earlier about using 2 to talk about 2 to the n as how often a population doubles. Well, the same thing happens with fractional things. I can talk about how often something is halved, right? Atomic atoms decay with half-lives. And so that's the same as 1 over 2 to the n. Well, why isn't it the same as 1 over 2 to the n? Why am I pushing everything downstairs here? And the rule we're looking at here I'm going to change this. What's on the inside? I'm reversing that rule. Well, if I now distribute my n, I have x to the nth and y to the negative n. That's the same as x to the n over y to the n. And that's the rule the book's going to show you. Is that if I have my n outside of a fraction, it distributes to each part of the fraction. And so these things can build upon each other. And these make the collection of our exponent rules. One more the book will show you. They'll say x to the y to the negative n. A negative sign says, hey, I'm on the wrong side of the fraction. It's saying everything in here is on the wrong side of the fraction. So we flip it. And keep that positive. All right. These are the rules. So I'm going to write down the rules. I'm going to use the notation that the book has specifically on these coming across. They all work from each other and they're all additive in their nature from PEMDAS. But let me write them all down together and give them some names. And so they all come from the same thing. So the first thing is our identity. Anything to the first is itself. I'll just say identity. And then we'll have the null for 0, which is anything to the 0 power is 1. All right. Then we're going to have a product rule. Which says if I have the multiplication of things with the two bases, I add their exponents. The quotient rule says if I divide things with the same bases, I subtract the exponent of the top. I subtract from the exponent of the top the exponent of the bottom. Then we have a power rule. If I take a base to a power, and I take the whole thing to a power, I multiply the powers. Product to a power, if I have two products, and I take them to a power, each component goes to the power. Quotient to a power. I have a quotient to some power. That power is distributed into the denominator and the numerator. then a quotient to a negative power. So I have some fraction to a negative power. I flip the fraction and make the power positive. And over here, negative power, I'm going to put back up here right next to the quotient because it came from the quotient rule. X to the negative a is equal to 1 over x to the a. X to the negative a is 1 over x to the a. And so these are the rules that we have to play with. Now, what I am recommending here is on Blackboard, I have the worksheets. Let's see if I can grab those here. We can get into Blackboard. It was fighting with me this morning. Last couple of days, the login goes okay, but when I go to actually click on Blackboard, it takes forever to load my individual classes. There you guys are. So let me see if I can show you this in a half decent navigation. So we can put this on. Okay, I'm going over to my browser now. Here is our section of stuff. And here is our course content. So in class practice worksheets. And chapter 15, the exponents and polynomials. This is what I would be doing for the last half of the class here. If we were in class, we would be working on this worksheet, right? This is definitely something that I think needs practice. So what I'm asking for you guys to do is to work on this when you're around this material. I know I'm recording. I might sometimes I'm 2 days ahead of where you are in the work. I'm a week ahead of where some people are in the work. And so when you're getting to this work, go through this worksheet. And right now we are up to, well, I would up to 5.3. Right, we haven't done a polynomial. So the first 2 sections of this, I would recommend working on and asking questions on it as a practice before you jump into the homework, because the homework works in different places. Because these laws aren't too hard to talk about, and they fall really naturally from each other. But I think it's hard for us to visualize what does it mean x to the third, that's x times x times x. Okay, x to the 6th is x times x times x times x times x. We're not used to stacking up multiplications like this and collecting those terms together. So we have to play with the rules a little bit until we can kind of shoot from the hip with them. The best thing I have ever found when tutoring people and working on this is to think of being one level down in PEMDAS. So if I'm multiplying 2 of the exact same bases, I'm multiplying, well, one level down in PEMDAS says that I have to add. So I add the exponents, right? And those exponents are hanging there up above. So you're kind of, the thing you do, if you think of ladder rungs on a ladder, have this showing here. Let me show this on a blackboard. We'll go with obnoxious red. So I'm going to have x to the 6th divided by x squared. All right, so I am dividing.
So I'm dividing. But I'm working with powers. And powers are up above. So my division is up above of what I have to do with them, which is subtraction. I will have x to the fourth to the fifth power. So I'm doing exponents. But my powers are up above. So this is up above what I have to do, which is multiply. And that's how I sort out these rules. That's how I remember how these rules work, is I relate them all back to PEMDAS and remember that I am up above, because I'm hanging out in the power. So I look at the rung below what I'm doing. If the operation I'm doing overall is a multiplication, then I'm adding exponents. So play with the worksheets, please. Bring me questions on the worksheets. If anyone has any specific questions, let me know. We're going to do the section on polynomials. We're going to do scientific notation and polynomials Thursday. And then in next week, we're going to work on adding, subtracting, and multiplying polynomials. And that will take us out here. I'm going to do these in light little bits, and I'm going to keep pointing back to using the worksheet to fill out the information and practice the different parts. Because conceptually, we're not working on the same level we did before, just like I did with PEMDAS. Hey, we're a level above. We kind of have to do this kind of split thinking because we're counting how many times we multiply. So we're using all our counting and addition and subtraction rules and our multiplication rules on powers. So there's a little bit of abstraction there, and I think the more you play with it, the better you'll get with it. All right, be safe, be well. I will talk to you guys later. Email me any questions. All right, and play with this stuff. Just listening to this and just watching to it, knowing why it is. This is something that for me, doing loads of practice problems, started to get it down because you don't visualize it, or at least I don't visualize it as easy as you should. I guess I visualize it a lot better now that I've done loads of it, but I remember learning these rules, and I remember just kind of like a WTF on what they mean, and then this is what they mean. And I guess because exponents go rather quickly, if we look at how a number goes exponentially, they get large really quickly. The things we're keeping track of get large really quickly in here. So it's really hard to hold in your head, but the rules summarize it really nicely for us. And so you just got to practice those rules. All right, I'm done. I'm done babbling. Have fun all.